Hello everyone, in this video we're going to pick up where we left off in section 11.1 with subsection 3, which is standard unit vectors. The unit vectors 1, 0 and 0, 1 are called the standard unit vectors in the plane and are denoted by a boldface I for 1, 0 and a boldface J for 0, 1. So what do these look like in the plane? Well, if this is my x and y axis, here's 1, make it a little bit bigger, here's 1, here's why is that not working? Ugh, come on. Here's 2, here's 1, and here's 2. What the I vector looks like is this vector right here. And what the J vector looks like is this vector right here. Right? So, again, this is J hat. Because I'm writing it down so I can't write boldface, so I put a little hat on it. You could put a little vector on it, depends on what you would like to do. And then this is going to be my I. Right? And again, it's because this is the direction of I, which has an x component starting at the origin and going to 1, and the x direction, and this is the j vector starting at the origin and going to 1 in the y component. These vectors can be used to represent any vector uniquely as follows. Say I have a vector which is v1, v2, then I can rewrite it as v1, 0 plus v2, 0, and then since v1 and v2 are just scalars, I can pull those out. Right? I can factor out scalars like going backwards with our scalar property, and then notice that I have 0, 1 and 1, 0, so I replace that with I and I replace that with J. Right? So any vector V can be written as V sub 1, or the first component times I, plus the second component times J. The vector V that looks like the first component times I plus the second component times J is called a linear combination of I and J, because linear because I have everything to the first power, scalar being multiplied, and I'm adding them, or I could have subtracted them. The scalars V1 and V sub 1 and V sub 2 are called the horizontal and vertical components of V. So V sub 1 is called the horizontal component, and V sub 2 is called the vertical component. And you can see why, right? I corresponds, V sub 1, which corresponds to I, is the x, or the horizontal, and V sub 2, which corresponds to J, is the vertical, or the y. Okay, so let U be the vector with initial point 2, 5 and terminal point -1, 3, and let V equals 2I minus J. Write each vector as a linear combination of I and J. Okay, so in order to find U, I'm going to go with my usual notation. I say U is equal to, and then in order to find my components, I take my terminal X minus my terminal Y, or my terminal first component minus my initial first component. So -1 minus 2, and then 3 minus -5. So I end up with -3, 8. Right? And then I want to write this as a linear combination of I and J. So the way I'm going to do that is just say I take my first component, which is -3, and I write that times I, plus my second component, which is 8, and I write that times J. And it's just as easy as that. All right, so it's just an alternative notation for these vectors. Okay, so how about W equals 2U minus 3V? Okay, so W is equal to 2 times U minus 3 times V. So let's keep these in the IJ format. So I have 2 times -3I plus 8J, because that is what U is, we just found in the previous problem, minus 3 times V, which is 2I minus J, given by the problem here. So now what I can do, and maybe this is a good way, that maybe this is one of the reasons why people like this notation, is it's easy to realize that that I need to distribute these values for I and j. So here, distribute these values to I and j. So here I get negative 6i plus 16j minus 6i plus 3j, which gives me, now I can combine my i's and j's. So I get negative 12i plus 19j. Right? And that was what w was, written as a linear combination. Right? I could also write w as negative 12, 19, right, in vector form. Okay, so if u is a unit vector, right, that means it has a length of 1. And theta is the angle measured counterclockwise from the positive x-axis to u, then the terminal point of u lies on the unit circle. Why? Because if I'm a vector, that means I'm centered at the origin, and if I have length 1, well, remember the unit circle is a circle of radius 1, right? So my terminal point is going to lie on the unit circle. And we have the falling. So let's see, how did they get that u is equal to, the first component is cosine of theta, which is a number, and the second component is sine of theta, which again is a number. So let's see how they get that. Okay, so let's draw our circle. I always do better drawing the circle first. So this is, say, my unit circle. So this is my x and y axis, right? And what are we looking at? U is a unit vector, so it has length 1, and theta is its angle from the positive x-axis to u. So this is, let's say this is u, right? And we know that since it's a unit vector, that this distance right here is 1. And this angle, let's start on orange since it's about there. This angle right here is theta, right? Because that's what we're given here. Now, let's think about something else. I can make this into a right triangle, right? And if this is a right triangle, I know that this length, or this distance of the length of the hypotenuse is 1. Let's call the length of this distance as x, and let's call this distance y, right? And if I find x and y, then notice that this is going to be the magnitude, or I'm sorry, this distance right here, y, will be the y component of my vector u, and this distance here, x, will be the x component, or the first component of my vector. So this is the second component of my vector, and this is the first component of my vector. So how am I going to find x and y? Well, I'm going to do it by looking at right triangle trig, right? So sine, or let's do cosine first. Cosine of theta is equal to the adjacent over the hypotenuse, right? What's the adjacent side to theta? Well, that's x, and the hypotenuse is 1, so x over 1 is just x, right? So we figured out that x is equal to cosine of theta. So this distance, x, is equal to cosine of theta, right? And now let's find y, and we'll do that by looking at sine. So sine is equal to the opposite over the hypotenuse, which is equal to the opposite is y over the hypotenuse, which is 1. So again, I get y. So I figured out that y is equal to sine of theta, right? So this distance is sine of theta, right? And again, this distance, the y, so what does this mean? This means that I can rewrite my vector u as the first component, which is x, which is cosine of theta, times the second component, which is y, which is sine of theta, right? And then writing that obviously in the ij notation, we get that formula there. All right, so that's where that comes from. Moreover, it follows that any other non-zero vector v making an angle theta with the positive x-axis has the same direction as u, and we can write it as the magnitude of that vector times the direction of u, which is cosine in the first component and sine in the second component. Right? So this was special because the magnitude of u was 1, so it made everything really easy. But in general, even if v is some really long vector, I can still have the same idea, except now instead of just having cosine and sine, I'll have the magnitude times cosine and the magnitude times sine. Okay, so let's look at example 6. The vector v has magnitude 3 and makes an angle of 30 degrees, which is equal to pi over 6 with the positive x-axis. Write v in component form and as a linear combination of the unit vectors I and j. All right. So v, what do we know about v? We know it has a magnitude of 3, and we know that it has an angle of pi over 6. Right. So I'm able to look at this formula right here and rewrite v in component form, right? But I need to know the magnitude. So I know the magnitude of v, right? And that is 3, and I know theta is pi over 6. So using that formula v, I know v is equal to the magnitude of v times cosine of theta sine of theta. And now let's fill in all those pieces. Right? So magnitude of v is 3. Cosine at pi over 6, because that's what theta is. Sine at pi over 6. I have to move this over a little bit more. So now what is cosine at pi over 6? Cosine at pi over 6 is radical 3 over 2. Sine at pi over 6 is 1/2. So I end up getting 3 radical, well, actually, gonna have to go to the second line. I end up getting here that I get 3 radical 3 over 2 and 3/2. So that's what v is. Oops. Right? So that is it in component form. And now write it as a linear combination. Well, again, that's pretty easy. I just say, okay, it's the first component, which is 3 radical 3 over 2 times I plus 3 over 2 times j. So that is my vector in component form. Okay, now let's talk about physics. So vectors have many applications in physics and engineering. One example is force. Why? Well, remember vectors are helpful because they have a magnitude and a direction, and force has a magnitude and direction, right? So the key here is if 2 or more forces are acting on an object, then the resultant force of the object is the vector sum of the forces, right? So in other words, if I have a force 1 and a force 2 acting on an object, then the resultant force is going to be the sum force 1 plus force 2, right? And that's the idea that we're going to use here for example 7. So say we have 2 tugboats that are pushing an ocean liner, right? That's these guys right here. Those are my 2 tugboats. And each boat is exerting a force of 400 pounds. Remember, force is measured in pounds. What is the resultant force on the ocean liner? So the idea here is that tugboat 1 has a force and tugboat 2 has a force. And if I want to find the resultant force, then what I want to find is the force 1 plus force 2, right? Okay, and given by the picture, just ignore this part here because I haven't done that yet. So ignore all of this. right? We're given the information. We know what the force is. Force 1 is going that way and 400 with 400 pounds, and force 2 is going this way with 400 pounds, right? Because this boat is pushing this guy at that direction, and this is pushing that guy at that direction, and that direction is I've got negative 20 degrees for force 2 and 20 degrees for force 1, right? So we can represent the forces exerted by the first and second tugboats as, well, force 1, how am I going to do that? Well, I need to write it in vector form because it's a vector. I know its magnitude because its magnitude is 400 because that is what force is exerting, and I know its angle, which actually we're looking at force 1, so I know its magnitude and I know its angle, so I'm going to use the formula that we looked at that's starred right there. All right, so this one's going to look like the magnitude of the force times cosine of theta sine of theta. Right? The magnitude of the force, again, is 400 pounds. And then we do cosine of, this time it's going to be 20 degrees. And then sine of 20 degrees. But actually, it might be better, since we're in this section, let's go ahead and use the IJ forms. Right? So remember, in the IJ form of this, it's the magnitude times cosine times I, and the magnitude times sine times j. So let's do this: magnitude times cosine of theta times I plus the magnitude sine of theta times j. Just because we're in this section. We could do it either way. The way I was doing it is perfectly fine, but just to practice, because we've done a lot of the component form, let's practice the IJ form. So then, again, this one would be 400 cosine of 20 degrees times I plus 400 sine of 20 degrees times j. Okay, and now how am I going to find for the second force, the force of the second boat? Well, once again, it's going to be the magnitude of the second force times cosine of that theta, I, plus the magnitude of the second force, sine of theta times j. Right? But this time, my magnitude is still 400, but this time my angle is negative 20 degrees. Plus 400, and then sine of negative 20 degrees j hat. Okay, and we can actually simplify this a little bit further, this second force, by remembering some properties about sine and cosine. So remember, cosine is an even function. So remember, what does that mean? Because it's even, that means that cosine of negative theta is equal to cosine of theta, right? And sine is an odd function. And remember, even means it's symmetric with respect to the y-axis, right? So that's why I get this negative. Sine means it's symmetric about the origin, which means that's why I get that sine. Whoops, let's go back to blue. Sine of negative theta is equal to negative sine of theta. Right? Or I could put parentheses around that. Those are some properties about sine and cosine that you're probably familiar with, you probably haven't seen in a while. So what does that mean? I can replace this with 400, and then instead of cosine of negative 20, well, cosine of negative 20 is the same as cosine of 20 because it's an even function. So I can replace this with cosine of 20 degrees. And then now, plus 400, and sine of negative 20, I replace with negative sine of 20. right? So I'm going to replace this with negative sine of positive 20 degrees J. Should put an I in here. So I end up getting 400 cosine of 20 degrees minus 400, or times I, minus 400 sine of 20 degrees times J. Now, the resultant force, that was what we were trying to find by the question, right, was the resultant force. The resultant force on the ocean liner is the sum of the two forces exerted by the tugboats, which is F1 and F2, right? So the resultant force, we'll just call it F, is equal to F, the first force plus the second force, which the first force is this, plus the second force, which I'm going to draw down here. I'm going to write down here so that way, because we're going to run out of room, is going to be this one. And now notice that I get this sign is going to, this sign is going to cancel out with that sign because they have the opposite SIGN signs. And I end up getting 800 cosine of 20 degrees times I, which is approximately, if I multiply that out, the next whole number is 752 or 752 I. So what does that mean? That in the context of this problem. Well, remember, I is like this direction, right? So what does that mean? The resultant force, and I could think about this even as 752 times 1, 0, right? Because that's what 752I is. Right? So the resultant force on the ocean liner is approximately, and the reason why I kind of like to write it like this is I see that this is a scalar, right? And the scalar means the magnitude, or which is why I know that it's in pounds, right? So it's an approximately 752 pounds in the direction, well, because it's positive, that means, and positive in I, that means in the direction of the positive x-axis, right? In the case of this problem, forward, right? The boat was moving forward, right? And what I covered up here was just what we solved for there, right? All right, and so that's how you can use vectors to solve force problems. All right, that's all I have for this video. Thank you.